Welcome everybody to our distinguished lecture series at Rutgers University in the Computer Science Department. This, I believe, is our second of this year. Third of this year. The second one that I got to be in this year. I was out of town, sorry. And my name is Michael Littman. I'm a professor in the Computer Science Department. And I don't know, maybe 2 months ago, 2.5 months ago, when we were looking for distinguished lecturers, I first thought of Sebastian Thrun, who is now a professor at Stanford University in the Computer Science Department. I thought he always gives great talks with lots of interesting visuals, and I also knew that sometime between the time I asked him and the time that he would come, he would win the Grand Challenge, the Darpa Grand Challenge. I knew in my heart that this was so, but I didn't want to jinx anybody and say it out loud. It turned out that, of course, I was right, and I've gotten a lot of glory for that. But not nearly as much as Sebastian has for actually winning the Grand Challenge. He's going to tell you all about it, so I won't give you a lot of background about the Grand Challenge, but let me say a few words about Sebastian himself. Sebastian, I first ran into him when I was a graduate student at Carnegie Mellon, and he was just starting out there as, I think, a research professor at first.
Researcher, actually.
A researcher. Having just finished up his PhD in Germany, and was going to join all the interesting learning stuff that was going on in the Computer Science Department at CMU. Over the next couple of years, he got a faculty position there and ended up staying for 8 years doing lots of really, really interesting work, including a number of very cool fielded robotics projects, including a robotic system that could actually walk around a museum, roll around in a museum and give people tours, guided tours, that involved interacting with the other people there, not running into things, knowing where it was, knowing the appropriate thing to say. Very big integration projects with lots of really fascinating scientific stuff underneath. That you can actually learn about if you don't pay attention to all the cool videos he shows. He did also, as part of that work, he ended up generating almost, I guess I give him credit for this, but I suppose there were other people involved as well, a whole research area on simultaneous localization and mapping, where a robot goes out and tries to understand the environment that it's in from the inputs that it has. After he left Carnegie Mellon and joined Stanford, the Computer Science Department at Stanford, he became the head of their AI lab, SAIL, and fairly quickly threw himself into the project of getting this Grand Challenge team put together, which took a fair amount of his time, but ultimately it seems like it was all worth it. But he'll tell us one way or the other if it was. So I want to give a very warm welcome to Sebastian. Thank you all for coming, and thank you, and I thank you. We look forward to it.
Thank you. How much time do you have left? Thanks, Michael. Michael has been a wonderful host. Really appreciate being here. I've been here in 2001. Is anybody here who saw my talk in 2001? Okay, one person. So you don't remember any of the animations I showed back then, right? It's good seeing you there. Okay, let's see, before I start talking about, who here has heard about the Grand Challenge before? Okay, so there's one person who hasn't, another one over there. Let's see, who here has a car? Yes, we did this one test. Who here thinks making cars drive themselves is a good idea? Okay, who thinks it's just a really bad idea? Okay, good, okay. So I loved your questions at the end of the talk, or during the talk, okay, because I want to twist your brain around and convince you it's a good idea during the talk. But before I talk about the Grand Challenge, a little bit of advertisement. This is actually what I'm more proud of. I actually published my book after 5 years of work probabilistic robotics, and if you want to understand what's going on, or just like equations, you can buy it. Grand Challenge. Okay, so there's 3 slides I have on putting it in perspective. The race was a desert race that Darpa designed in 2003, first executed in 2004, with originally $1 million prize money and then $2 million prize money. Idea is to do something that at the time people thought were impossible to do, which is build a car. It drives itself without any human intervention, even without a human inside, through more than 100 miles of desert terrain. Desert terrain because DARPA has an interest in a military organization in driving in places like Iraq and Afghanistan, and they felt that having an empty desert without other vehicles around would be a realistic scenario. And DARPA, as I show in the next slide, has spent significant money trying to build this capability for the military, but has failed in achieving this. They put a prize money out there, $2 million, and as such the event is related to a number of achievements that were attained through prize money. competitions. And here's a small number of those. It's hard to compare. I think all of these are much more significant than what we did, but all of those had kind of the same public perception and people sitting behind a laptop, for example, or a web browser and following up. I remember when Deep Blue beat Kasparov, it was my biggest day in the year, just watching it happening and following every move. And from Darpa's perspective, the idea, as I just hinted to, of building unmanned ground vehicle is an old one, goes back to the early 90s. And Darpa must have spent in the order of maybe $300 million or more on funding on this over the years. There were a number of programs that originally in Darpa moved into the Army Research Lab, ARL, known as Demo 1, 2, 3. In 2001, Congress mandated that a third of all ground vehicles be unmanned. Unmanned doesn't mean that they drive themselves. They could still be remotely controlled, but they would have no person inside by 2015. And the type of performance you'd see in these demos would be in the order of 5 miles per hour. Human intervention often every half a mile. And of course there was significant funding involved. So DARPA had this fantastic idea. Let's turn this into a faster speed, so 20 miles per hour, which is the speed necessary to formally win a grand challenge. Let's have no human intervention whatsoever as opposed to frequent human intervention and have no funding. And it worked. So they got what they wanted. Let's see. The thing that excites me personally much more is actually not the military dimension of this, which I have to admit I'm somewhat ambivalent about, and I've been quoted in the media for being but much more the civilian perspective. To me, the automobile is a relatively young invention. It's about 100 years old, or maybe 120, depending how you count. And it would be foolish to think about the automobile staying the way it is today for the next 100 years. So there'll be innovations happening. One of the biggest problems in driving is it takes away a lot of productivity. If you commute, say, to New York City, you know it takes, I don't know, rush hour, maybe 2 hours or so from here. It's not a pleasurable driving task. In fact, I just took the train because I could work on the train. So if you could turn a car into a train-like instrument where you sit inside just like in a train, but combine it with the convenience of having your own personal car that brings you to the place where you want to go, and turn every road into a kind of railroad, then you could actually really revolutionize the way we deal with spaces. So specifically, commuting in the US is estimated by the Texas Research Institute to cost us $61.1 billion annually in terms of loss of productivity. And that's something I think we should, as a society, recapture by building robotic technology that can assist drivers and later overtake off driving tasks. Not necessarily all of driving. I think there's still a space for having your Porsche and go on a highway. But maybe parts of it, the parts we don't like commuting. If you also look into the automobile as an invention, traffic accidents in the US kill about 43,000 people every year. The number is going down, which is good due to the number of safety measures, but it's still amazingly large. If I were to stand here and ask you, I have a new invention, it allows you to get from A to B faster than trains, but it's going to cost you 44,000 people a year, and then ask the question, do you think it's a good idea or a bad idea? I hope everybody would raise their hand and say it's a bad idea. But that's current status quo. We're actually tolerating the loss of many of our friends and family members in doing so, and huge number of injured, and it's actually the leading cause of death for people of most of your age. I'm slightly older than you are. By building automobiles that drive themselves, there is a perspective to make the vehicle safer. Safer because nearly all of these accidents are accidents involve human error. About 1,500 of those involve collisions with trees. Okay, can't really argue this is not human error. Flip over, rollovers with SUVs and so on is a very large number. I'm not saying we can set this number to zero, but we might be able to substantially reduce this number by having more intelligent cars all the way to cars that drive themselves. So that's the vision. There's more visions to it. If you have cars that can drive themselves, they can also park themselves, which means you don't have to have your parking lot right next to your office building anymore, which means you can change the way you use real estate. Or you can go to the airport and drop off your rental car and it parks itself. So there's all kinds of future visions. If your car would be able to drive itself without a person inside and get to where you are when you need it, that you could make your more effective use of vehicles, of space, and so on. And if you think this through, and not saying this is all happening, but if you think this through, then the revolution will be larger than, say, the revolution of the internet. So the Grand Challenge didn't achieve any of this. It's just a very small puzzle piece, and this is a specific race. So let me tell you more about the race itself. And by the way, if you have questions, please feel free to interrupt. The race involved basically a course that was given to you in forms of a sequence of GPS points, GPS coordinates, about 2,700 of those, about 2 hours before the race started. The 2 hours gave you time to look at the data file and put it into your robot. And then the robot had to be a button push, been able to drive this route by itself. It was followed by a chase vehicle that had an emergency stop system, a wireless emergency stop, in case the vehicle did something very, very stupid, like run to a power pole or drive off the course. But the expectation was that this stop would never be used and the vehicle would just go by itself. There was some logistics. Sometimes vehicles pass each other. To avoid dynamic passing where two vehicles race, Darpa would pause one of the two cars, maybe the one that's currently being passed, so that the second one would pass a static obstacle, as happened to us, but the time stopped or paused would not count against the team. So in total, the team that was paused wouldn't lose anything. And that made it a time race, not a race for arriving first, but arriving in the shortest amount of time, and also made it a static world race, which is you never had to deal with other traffic participants. So that's the most important unrealistic assumption relative to the divisions I just discussed. Okay, so here's an example of last year's RDDF file, just to discuss it with you. This is kind of the input we got to the system. There's a lot of wire points shown over here, little crosses, and these crosses, when you connect them with straight lines, turn into a corridor. There's two more important informations here. One pertains to the width of the corridor that varies between about 8 meters and 1/4 mile. So right now it's a relatively narrow corridor. And one pertains to the speed limit. The course itself had speed limits that were mandatory. They went all the way up to 50 miles per hour. So you see a wide area, passing zone maybe. And the speed limit was mostly there to protect the environment and to protect the chase vehicle behind the robot. It turns out chasing these robots can be really tricky, specifically if it's very dry in the desert and you stir a lot of dust. So many of these speed limits were relatively conservative, like 25 miles per hour over here. So from that, you had to turn it into action.
How fast could you have gone?
So the theoretical limit this year competition was 50 miles per hour, and we went 37 or 38. Let's see, now I lost my train of thought. The key thing is, you are in a car, you have basically 2 degrees of freedom. You can go left or right. That's one control you have, and you can go faster or slower. That's the other that you have. So the trick was now to take a corridor like this and turn it into action. It's not as trivial as it might look like, because this corridor doesn't exactly specify the road. It doesn't specify a specific obstacle. So it might well be that inside the road there is a huge obstacle, or it might be that the corridor is very wide and the road is just a part of it. So you still had to understand the environment. This was more like a rough guidance where to go than a specification of how to get there. Okay. So this is last year's Twin Chance video. It's fun to watch. Last year we had a little more than 100 teams that participated, and about 70 that made it to the final race.
And we're 30 seconds from history.
There's a lot of history talking about.
Ladies and gentlemen,
Carnegie Mellon, the college in Pittsburgh, did quite well last year. Was the best one last year.
Amador 2004, ladies and gentlemen. Elbit Cyatonics 2.
Okay. What you see is that a number of teams built their own vehicles. About half of them would use
ladies and gentlemen from Caltech.
Pickup trucks. Others wouldn't. This is a car that's too slow. It's a local Silicon Valley startup company. Did quite well for the first mile or so. Virginia Tech. This is kind of a half homebrewed vehicle. These guys loaded the wrong RTDF file, the wrong GPS wirepoint. They thought they had to go back to San Diego. But they couldn't, because it was very turned around and went back to the starting chute.
University of Louisiana at Lafayette.
Louisiana, if you look at this, that speed is completely insufficient to win. It would take maybe 30 hours, and you have a time limit of 10 hours. Team Ensko had a control problem. They actually flipped over, right over here, but the Darpa video stops just before the flip. So it's just during the flip.
From Gainesville, Florida,
if you go on
and Logan.
a little bit further in this video and look at some of the lower
Up we go with Terramax, ladies and gentlemen. 32,000 pounds, 6-wheel
Okay. One could argue whether this is a right vehicle or not, but certainly
Okay,
a very good
ladies and
navigation
gentlemen,
platform.
launch on column 1.
This is UCLA. And this is my favorite from Berkeley. We call it overseas from San Francisco because
The
it's
wire
bay in between.
demonstration.
Berkeley put in a motorcycle.
Off we go.
Okay, Anthony Lewandowski, I'm actually a big fan of him. He's a great student. I was joking in the talks before the Grand Challenge that this year they're planning to double their performance. Okay, this is the end of the 2004 Grand Challenge. And this slide really says a lot about what this race is all about. If you look very carefully, you find a desert road. This is actually a fairly difficult terrain already. It's steep. There's a big slope from here up here, down here to the valley. You can see the runoff. And the road here is perfectly drivable for everybody. I mean, you can take a mountain bike and have no problems, and of course a regular car has no problems, like a pickup truck. But what happened is Carnegie Mellon went off the road, following the GPS points, and off the road, not even a tank would recover. You basically fall down, and it'd be really hard for you to get back on the road. So it's really about staying on the road. Okay, so if you stay on the road at the right speed, you win the Grand Challenge. Okay, that makes it a software race. So vehicles like off-the-shelf SUVs are perfectly capable of doing this. What you do is you take the person out of the machine and put a brain in there. So it's really about the sensing, computing, and then action of giving steering to the car. No more, no less than that. So if you approach the Grand Challenge, as about half the teams did, by building a new piece of hardware, you might have invested your time slightly at the wrong end. And then in hindsight, the teams that actually did very well had all commercial vehicles. Just for history, 2004 we had 106 teams competing, all US-based. 2005, okay, see the difference, 195, almost 200 teams, 3 international teams. Darpa actually selected them down using site visits down to 43 teams in May this year. We survived that. We were very happy to do this, to make it to the site visit. And then there was a qualification event where 23 finalists were picked. Here are the finalists, and we also made it to that qualification event, which made us very happy. Here's some images of the qualification event. This happened in September. The idea was to have on a parking lot, essentially, a mock-up Grand Challenge. Let me switch off the sound here. It's our car Stanley. It's a Volkswagen Touareg at Stanford. You can see our sponsors are. We got sponsorship from Red Bull and the venture capital firm and Volkswagen and a company that's now part of Google. No defense contractor, by the way. All like, okay, the winners are Red Bull, drink manufacturers. There was a high-speed section where you can do high-speed driving. This is about 35 miles per hour here. Car is completely autonomous and is able to avoid obstacles at that speed, so it's relatively fast. There were sections that kind of resembled mountain passes, underpasses. There were 3 underpasses on the course. Underpasses are hard because you lose your GPS coverage in underpass, so here's an artificial underpass. And before that were hay balls that kind of symbolize maybe plants or rocks on the roadside, and many of the vehicles love those hay balls and love to go into them and ignite them and put them on fire. We actually made it to the site visit. There were about 4 runs we had to do without touching anything. So at some point we were called Team Boring because the cleanup crew never had to clean up anything behind us. But we weren't the fastest. In the end, we were second, set numbers 2 in the race, the second highest vehicle. If you look at other stuff that happened, this is a video from Car TV. We had a lot of media coverage there, so I steal most of my presentation material from the web. You can see different types of vehicles. This is Caltech. Here you see attempts to go through a berm. Berms are very hard to see, by the way, for any vehicle. Let's see, there's some site qualification event videos coming in a second. This is Carnegie Mellon. This is Pittsburgh-based college. So here's the hay ball action, another bit of hay ball. We should remind ourselves that these are actually images of vehicles that are completely driverless. So they look sometimes very, very stupid when they run into a concrete wall, for example. But if they don't see it, they just don't see it. There was one vehicle that actually drove quite fine and missed the waypoint, and then decided to come back and chase that waypoint and turn around and confused everybody and circled around the waypoint for half an hour. Race day. This is now the 23 teams selected out of the 195 that got permission to race. It's 6 o'clock in the morning. It's Primm, Nevada. The race this time was a circular race. It went from Primm out into the desert, back to Primm, out into the desert again, back to Primm. And it was mostly flat land, which kind of disappointed us a little bit because we've kind of trained for harder terrain. It's Carnegie Mellon here taking off with their first vehicle. They have 2 vehicles in the race. We only had 1 in the race. But there was also some mountain pass called beer bottle pass at the very end, and it's a good name because at the time it meant to beer bottle pass. We all had drunk a lot of beer. Here's Stanley taking off into the desert. Little swerve that surprised all of us. We had, I think, no GPS in the beginning. We had some GPS problems, no clue of what caused them. But as soon as we left the starting area, our GPS kicked in again, and everything was fine. It's a big feeling to build a car like this and have it go into the desert and disappear. So you sit there, and this is your car. You put a lot of money into it. It goes by itself. It's like sending a kid to college. And at some point, all you see is a little bit of dust, and next thing you see is a helicopter. It's not like kid to college, okay? It hovers over your car and that disappears, and then you sit there and wait. It's a very strange endurance race because endurance races in the past always involved technology and people. Like if in a balloon around the world, there's a person inside the balloon, right? Here, the moment the race starts, the person is completely irrelevant, and the robot makes all the decisions. It's kind of a little bit of an interesting dimension to us too. So the race went on. For us, like the rest of the world, there was just a simple computer display where you could follow the race, and you'd see it in a second coming up. A website that some of you might have seen. I don't know. People check the website in the day? Anybody? Yes, some did. Good, great. Dinesh did. It's cool. This is a video we couldn't even see ourselves. It's taken by Darpa. We only got it after the race. The webpage had little dots on it that showed how far the teams had gone. And you could follow and follow our dots. So this is our dot, okay? This is Carnegie Mellon. You can see how we bump into Carnegie Mellon. Then they stop us so that we wouldn't run over Carnegie Mellon, and then they would accelerate, and as we came down here, they actually let us pass Carnegie Mellon. So at mile 102, there was a voice in a tent full of people, like maybe 500 people saying, "Ladies and gentlemen, I have an announcement to make. Stanley just passed Carnegie Mellon's Highlander." And you can imagine, like, 3/4 of the people were completely enthusiastic, and 1/4 sat there very sad. This is the Highlander as we passed it. This is a video image from the vehicle itself, from Stanley. After the race, you could upload it and visualize it. During the race you couldn't see this, but here's basically one of the many routine moments where our car passed a static obstacle. The static obstacle looks like a lame Hummer sitting on the right side. I should say I used to work at Carnegie Mellon, so I make fun of Carnegie Mellon for 8 years. It's a great place. This is how Carnegie Mellon Hummer looks in 3D using laser range data and so on, and then we just move on. Carnegie posted the same video from their perspective, so you can see our car passing, right? But I don't have it here. This is Beer Bottle Pass. Darpa put a movie crew up there that did live video feed into our tent, so you could actually see this live as the car descended through this relatively steep mountain pass. There's a 200 feet drop off on the left side, fairly steep at times, and it kind of symbolizes if you think about the race as building a stronger car, no car would really survive falling down over here, even if it's not that steep. Over here, it gets steeper back there. But if you're on the road, even a blind man could drive down the road. So it's really about perception of the terrain. This is Darpa's chase vehicle.
Yeah. Is it braking or just gearing?
It's braking. It's braking a lot. So it has a fairly elaborate velocity controller that makes sure the velocity is kind of fit for the terrain. This is, I think, a 10 or 15 mile per hour speed zone, which means you can go a little bit faster than it actually goes. But we found out going fast in areas like these can be very fatal. So having it a little bit slower and losing a few minutes was better than falling down the cliff. But you can see it's relatively steep on the side. But what's nice about the road itself is very flat. There's no tumbleweeds, there's no desert turtles, all the kind of things you could encounter. So that makes it relatively easy. As soon as you know where the road is, as long as you know where the road is, you're basically fine. And then there came moments, of course, where we were sitting there, we saw the car descending the water path in the tent, and then it disappeared out of the field of view. Here's more of the same. And then we all went to the grandstands, waiting for about half an hour for the car coming out of the desert. First thing you see someone, so there might be a helicopter at the horizon, or the helicopter hovering above the car, taking video footage. Okay, you see the helicopter come out, and then 15 minutes later you see a little dust cloud on the ground, and you realize, wow, it's going to make it. And then you start praying, and then it comes closer and closer, like this. It was a really big moment. And there's Tony Ted on the left, waving his flag in a sec, as if the car would be able to see him wave a flag. So there's a person inside, but he does it anyhow. And then the car gets reactivated and gets into this. This is us over here, standing from the car's perspective, so I'm somewhere over there. And then all of a sudden I get drenched in water and ice water, and find myself on some shoulders of people. And it's just been a really big moment. I think it's a big moment for all of us, the entire field, because we've been really working hard, these 195 teams, to make cars drive themselves. And the fact that the fact that we got our $2 million check. In fact, I got the envelope in here, and Mike got this big, Mike, my postdoc, got this big pseudo check. I got the money. But I think it was significant for all of us because we all fought to get a car back home. And in the end, 5 cars made it. In fact, if you look at the final board, we just made it with about 11 minutes ahead of the next team. The margin is so incredibly small because we're all driving right at the speed limit dictated to us by Darpa. And that was an amazing success for a huge number of teams. If we look at these distances, I think more significant than us winning, and we won with a good amount of luck, I should admit, is the fact that so many teams actually made it. This is really changing something in Washington right now. People are realizing the dream of self-driving cars is much closer than they thought it would be. It's actually, we are not there yet, but it's actually much more feasible within 2 years of no funding. What I want to do with some of the time here is actually go into some of the science that's behind and the tricks we played. And it's somewhat preliminary because we're still evaluating what are the key elements that made it happen. Stanley itself, here's a drawing that's going to come with the public mechanics in a couple of weeks of Stanley, with interiors. You see a computer box in the back. Let me hit another button here. See, oops, wrong button. Okay. There's an inertial measurement unit, multiple GPS systems, one for finding out where you are, one for finding out what direction you're heading. It's a compass, GPS compass. Emergency stop, laser range sensors, I'll show you those in a second, a camera, a radar system we have not used during the race, but we had it anyhow, and what's called a drive-by-wire system, which is essentially the interface to the car, where you can basically control the throttle, the gas, and the steering, and gear shifting all electronically. One thing that every team did, really every team, was to do what's called position estimation or guidance. We have a car drive along. Luckily, US put satellites in space called GPS navigation satellites, same you use in a navigation system in your car, and you can measure basically where you are using very simple GPS systems. There's nothing new here. And what's common in all of guidance, missile guidance, ship guidance, and so on, is avionics guidance, is what's called an inertial measurement unit. It's a little box that measures accelerations in 3 dimensions and rotational velocities in 3 dimensions that allow you to fill the gaps between multiple GPS measurements. And that gives you kind of an estimate where you are relative to the course about 100 times a second. Okay, it's really important because you want to know where you are, what direction you're headed, because if you're headed the wrong direction, you want to take corrective action in your steering. More interesting is the environment sensing part. This is a little depiction of the laser system. Oops. Every time I do this, it gets stuck. It takes some explanation. On the roof, there's 5 laser systems, and we take the data here and color them differently just for convenience. Blue, yellow, green, and red. I think there's 2 blue ones. You can only see 1 here. What they do is they send a laser signal on a mirror that's tilted. The laser goes out to the world, gets reflected, and you can measure the time until the light comes back into your sensor so accurately that it can determine range up to an inch accuracy. It's really amazing. So I could take a scan of this lecture hall, and if you looked at it afterwards, you could see all the walls and the beams and so on, very clearly in some of the 3D point cloud. Now, the mirror itself is actuated, it rotates 70 times a second, and thereby allowing the laser to scan the terrain. Right? So as it rotates, you get more and more scans. So what these things are little stripes that the laser acquires as it went, and you can see the frontier of the stripe over here. If you just memorize them over time, you get these 3-dimensional maps that are completely 3-dimensional point clouds. And you can see now how these point clouds build. Here's one laser pointing at the ground, another laser over here. Sometimes the V goes up and down. That causes these bands of data. I'll comment on this later on again. That's laser. Second modality, just for completeness, is camera. We had a video camera on there on the roof. This is how video footage looks of last year's Grand Challenge course. It makes you seasick, but that's what is being used. The nice thing about the video camera, you can see further, so sometimes you can see the road immediately at the horizon. So the trick is to see if you can use the camera for seeing further than lasers can watch. Let's see. Then there's radar. The interesting thing is happening on the right side, not the left side. Left side is laser data turned into a map, but the right side shows radar readings. Radar is reflective by big water objects or metal objects, coke cans. So we have a wonderful coke can finder. This is a telegraph mast over here. We use this also as a long-range sensor to detect abandoned vehicles at a range. Yes?
Do you have any problems with dust, like getting kicked up by other cars?
Yeah, so dust makes our sensors gradually more blind, which means we drive more aggressively as a result. True. So the vehicle in the beginning of the race is very inhibited, and at the end of the race, when all the lasers are dusty, it becomes very, very aggressive in driving. The bigger problem is water. We had significant water on some of these courses, even in the summer. Mud gets into the sensors. We had a little cleaning mechanism for our camera to accommodate water, mud, and dust, but not for the lasers. Puddles are also problematic because puddles swallow laser light, so you get no reflection. You think a puddle and a cliff are indistinguishable, so sometimes you have to be a little bit courageous. This is stereo. You might have seen. See any stereo researchers in the room? Good. Okay, thank you. Because I'm going to make some negative comments in a sec. But the stereo, we tried the physics, which is a really world-class stereo. And when you do stereo, you get these depth maps, and they look very impressive. But when you turn to the 3D maps, you realize they're complete crap usually, and unusable because all the ranges are wrong. Stereo is a very hard to control modality. In fact, I used to joke stereo doesn't work, and actually it doesn't really work. So we ditched it. Here's range data. So what I'm going to do is I'm going to go through two of these sensors, range data and cameras, which are the two most interesting ones, and tell you a little bit about the problems that exist when you want to interpret the data and how to accommodate these problems. This is a single laser pointed forward, about 20 meter. It hits the ground. Okay, you can see the ground, and you can see the bushes on the side. You can see large areas of occlusion where you see nothing. Okay, and one of the interesting things you'll notice is there's lots of bands here. Okay, like the one over here, one over here, one over here. And these come along because you think maybe the terrain is hilly. But even on totally flat terrain, you get those bands. And the reason is, every time you brake a little bit, the vehicle goes down. Okay, that means your laser scans closer to you, and then you go up again, it goes out again. Okay, so you scan the same terrain twice sometimes, and then you don't scan other terrain as well as before. So here's my little depiction of how a laser works. We point it at the ground to see the drivable surface and the obstacles. Normally the vehicle just goes forwards and scans the ground, and you can create a 3D model. In fact, you can look at obstacles. Here's a typical way to act obstacles. You go forward, and then you realize that there's a point that you sensed over here and a point you sensed over there, and their vertical difference is more than 15 centimeters, half a foot is our threshold for obstacle sizes. So this looks like an obstacle. So from these 2 points you have a witness, abusing Mike Waldman's thesis language, a witness for an obstacle, because you have 2 data points that are in a configuration. They're relatively nearby XY space, but have a difference in elevation of more than 15 centimeters. And that's the place where you don't want to drive. Okay, so all of mapping is about this simple. If you find a witness to an occupied location, then you don't want to drive there, okay? Or you're less likely to drive there. So if everything's occupied, you keep driving anyhow. So here's the effect of the vehicle pitch that I just explained. Go forward, and now the vehicle pitches for whatever reason, and it pitches all the time. I mean, even normal cars pitch all the time. And if you drive through the desert, unpaved roads, you pitch all the time. And then you go forward, and what you get is an effect that you actually scanned area twice. This is actual data from the 2005 race. We took just the middle beam of one of the lasers and plotted it from the side, and you can see the vehicle pitch a little bit, okay, with the waves. And there was another one over here, another one over here. You can see these things where it goes back and forth, okay? And some of them can be very drastic depending on how much pitching action is involved. So we have a calm series now. It's going slower a little bit. Another pitch, okay? Here's a bigger one, okay? That's still fine, still less than 15 centimeters. But then you get these moments where all of a sudden your model goes wrong. And I stopped it here. What happens here is the vehicle had some very severe pitching actions, which happens all the time. And our estimate of the vehicle's pitch was not exactly accurate. We were maybe half a degree off. But if you extrapolate this out 20, 30 meters, then half a degree can give you a map that has a vertical deviation of more than a meter. So here we have a witness for an obstacle, which turns out to be flat terrain. And it leads to very interesting behavior. This is with us driving in the car, and we have to make all these judgment calls. So here's a map being built at relatively low speed. We're going about 10 miles per hour. There is our little pitch problem. Red means occupied, if you haven't guessed it by now. And now here we go. And this actually happened. This is on the old Grand Challenge course. When this is a cliff, we typically hit a red button before we fall down the cliff. But in this case, there were just bushes, and we don't care about bushes. We just went into those and kind of recovered. But you can imagine this is very frightening. In fact, my students worked on this for about 8 months, trying to find the perfect mapper, and you can see red bands all over the place. This was a frequent phenomenon. In fact, in some of our data, the number of false positives means cells that should be marked as drivable, but we have a false witness, are about 12.6%, a huge number. Another one over there, right? And all of those over here. So with this we could drive maybe 30 meters without fatal error, but no more than that. Okay.
Sebastian?
Yes.
So could you use the IMU to correct for the pitching?
We are using the IMU for correct for pitching.
This is after.
Yeah.
How much of a mechanical solution did you apply to avoid this problem?
How much problem?
A mechanical solution did you apply to avoid this problem?
What mechanical solution would you
Like a
suggest?
gyroscope, you can change
The vantage point?
in the same place. Well, how much did you apply to that?
So you could lift up your sensor. The problem you're going to run into is that the assembly that lifts up your sensor might not be very sturdy, and they would introduce additional torsion, additional uncertainty as to where the sensor is pointing. So we had to do it in a very sturdy way, and we had still fit under underpasses that are 8 feet high, which is a bit of a tricky thing. So to be able to drive it down again. Building a mechanism like this is much more involved than the 3 lines of code I'm going to show you in a second that fix this. In terms of IMU, we didn't have a weapons grade. We had weapons grade IMU, like an 8K IMU, $8,000, but not a $100,000 IMU. And maybe a $100,000 IMU would have reduced this problem, but in all likelihood not eliminated. So this was a real problem for us, and we spent enormous amounts of time trying to get rid of it. It's not just a footnote. This was maybe the most significant problem we had. We did a lot of tests to understand what's actually going on, what causes this problem. This is data taken from a straight road where we look at the z deviation over here. I'm really late. And ask ourselves, the straight road, we know that the z deviation should always be 0, but some cells are flagged as 10 centimeters, 20 centimeters, 30 centimeters. Everything from here on is lethal, and so it's colored in red, and that's about 12.6% of the data sits up here. And then we realized there's a correlated factor to this, which we found, which is the amount of time elapsed between you saw the bottom witness and the top witness. In fact, if that time is 5 seconds, in all likelihood your estimation would be entirely off. If the time is only 0.1 seconds, in all likelihood your estimation is very correct, which suggests there's a very slow modulating noise curve over your position estimation. That was nice because if it's slow, we can actually estimate it and compensate for it. And the idea was to build a little Bayesian network. This is the standard pose estimation network where you estimate your state at time t, t plus 1, t plus 2, and this is the state, 12 dimensions of pose estimation, so 6 of pose and 6 velocity, and you have like GPS to feed into this and so on. Build a little, and normally in the old scheme we would just trigger if we find obstacles whose z derivation is more than 15 centimeters. But let's see, let me go here. The idea was to build a Bayesian network that models the decay of information over time. So there's some error at time t, some error at time t plus 1 and t plus 2. This error propagates, it changes over time, we lose information, and then there's also error related to the measurement itself, and we would try to model all of these things in a probabilistic manner. And then instead of saying we have to find 2 points that are 15 centimeters apart, now we have a probability construct, so we can only find 2 points which are 15 centimeters apart with a certain probability alpha. Okay? So to visualize this, what this means is for our witness test, if we get 2 points of the same location, okay, these are 2 points of the same location with a different z value, okay, but at different points in time. A simple test would just say we ignore the time, oops, let me go back here, we ignore the time and just take the z deviation, and that happens to be this difference. But the new test says over time you lose information in a linear fashion. So you lose some initial information because of sensing noise, but then you lose more and more information. So when the second measurement arrives, this is the real z measurement that you can do up to some certain confidence threshold. So as time goes on, you're less and less confident about where the point actually was relative to the previous point. This is nice because it lends to a very efficient implementation. When you get a second measurement for this point, this is strictly more constrained than the first. You can throw away the first witness and just retain the second witness. If they partially overlap, you can retain a combination of those to end up with basically a set of bounds that you propagate forward. Now, this probabilistic model had all kinds of variables involved, where you had to specify how fast information decays and so on, what's the initial error, what does it depend on, lots of functions. You could sit down and carefully craft it, but the physical process underlying all this is so incredibly complex, it involves satellites in space, you could just also go and learn it. So we decided, instead of trying to fill all these parameters by hand, and I apologize for being somewhat fuzzy here with all the math, but I tried not to put any math in the talk. We said let's learn these parameters automatically. So let's set up a learning procedure whereby we can find out exactly the rate at which information decays, and exactly the rate at which, let's say, pitch uncertainty comes in, and the actual pitch uncertainty in a measurement, and so on. There's a couple of parameters. Now, how do you learn this? Well, for learning, you need data. Okay, so we set up a discriminative learning routine. And how to get data, says the code, what exactly is big care of information. And there's a very simple trick that you can play for getting data, which is embarrassingly simple, but very effective. It involves human driving. When I, as a person, drive my car, okay, what I drive over is flat. So a perfectly tuned system that perfectly decays information should always predict that there's no witnesses for obstacles at cells where I drive over. In fact, the z derivation for any cell drive over should be 0. Okay. Now, that alone is insufficient. So it means I can go and take the car for a spin and collect training data. It drives 3-4 minutes, and I have thousands and thousands of examples of grid cells and so on. I can tune my system so it says flat over here. That's now artificially colored white. But that's not sufficient, because a system like this would basically reject every obstacle and say information decays instantaneously when everything flat. We still wanted to say occupied somewhere else. So I defined this pseudo margin between 2.5 meters out and 4 meters out and just call it all occupied. It's a bit of a lie, because some of the terrain on the side is not occupied, but by pulling a system so that it says as free as possible over here and as occupied as possible over there, I get a really nice parameter tuning. So here's before and after. It should be the same data. You see a band over here, another one over here is missing now. Okay, so this probabilistic model / learning thing got us from a failure rate of 12.6% to 0.002%, 1 in 50,000. So it's quite a significant change in performance, which means before we had an encounter every couple of meters, now we have an encounter every 20 miles. One over here. Still too much, but that actually was a huge day for us, because all of a sudden we could drive and see terrain with the laser stitch forward. Okay, that was the laser part. Let's see, it's 10 to 12. What time should I finish?
We started a little bit late. Seems like we got to be able to go until
12:05, 12:10?
Yeah.
Okay.
12:08, I heard.
12:08? Okay.
And 42.
Any more bids? Okay. Someone says now 11:55 will be insulted.
Somebody hit an obstacle.
There is an obstacle, like an empty lecture hall. Okay, I mean, I became professor because I love to talk, right? So, that was a joke. No one laughed. That's embarrassing. Okay, so the problem we ran into is we had to push velocity. So it turns out the lasers with this kind of logic can see about 22, 25 meters out at best. And we did extensive testing on a South African gravel, which is a very smooth gravel that Volkswagen uses for testing their Touaregs. And we could only come to a full stop at speeds of up to 25 miles per hour, which means it would be unsafe with obstacles at higher speeds. At the time, we didn't realize that the course would be so easy, there would be no obstacles at higher speeds. So we built a car that actually would be safe even at higher speeds. And we did some strategic calculations to figure out that if we did 35 miles per hour, we'd be fine. Pushing more, given the speed limits of the Grand Challenge, would not buy us significant time, yet increase the risk of failing. So we set 35 to be the final goal. And the idea here is use vision. And here's a little image I just want to show you from the race, which this is taken from the robot itself, and we could only see it after the race, but we can obviously guess what's going on. It's trying to find the road. Ignore this little crazy trapezoid at the bottom, but that's kind of the labeling of road that you can get out of the vision system, which I have to admit, when I saw it, it's probably the wrong word to look at your own research and say you're impressed, but it was basically Hendrik Dahlkamp's and a couple of computer vision research from Intel that did this, not myself. And I was quite impressed, I have to admit, that you can actually see roads as well. This is all like dirt, right? The dirt color from here to here is almost indistinguishable.
What are we seeing?
That's the result of a computer vision routine trying to find the road.
And how do you define road?
Road is red and non-road is
I understand
green.
how it's displayed, unless the road actually is green on the side. I mean, presumably it's making some kind of judgment call.
Yeah.
What is it basing the judgment call
Oh, I'm just about to tell you.
Okay.
But now that I have your full attention, let me talk about it. So we tried a number of things. The first problem that we ran into is what actually defines a road. And we had a really hard time. These are all images from last year's course to come up with a criterion what makes road road. We started out with color and said, okay, we go for brownish color, but then as soon as you go on pavement, that doesn't work anymore. It's embarrassing to be slow on pavement because that's where you should be the fastest. Then we said, okay, maybe it's smooth and maybe it's texture, maybe the stuff on the side has more texture than stuff over here. We implemented that, and all of a sudden the sky became road because it's the least texture. So in the end of the day, we couldn't find a piece of software that gave us a road detector. In fact, it's a bit of embarrassment for artificial intelligence if we talk about, how we make human level intelligence and reason about objects and blocks and so on. And we can't even define this, the most primitive thing, which is road, okay? And you're on a road, so should be able to define it. Now, we went through a couple of ideas using machine learning. We could have done the same as before, just train the system by manual driving. But what we ended up doing is more an online training system that kind of had a self-labeling data aspect. I'm going to skip through these 2 or 3 slides because it's not what we did. The idea of the online system was, let's see, a bit like human learning, because when you're a little shy and you touch the hot stove and you get this amazing pain in your finger, you might be learning something like, something that looks like dark red and seems to have like some air distortion on top of it and feels hot. When I go further with my hand, it will hurt me. So you do a transfer of the association of your sensor data from your finger to your eyes, or maybe your other sensors. So here the idea was, we already have a perfect road detector or a system that can tell us what is drivable at near range when it's kind of too late, called the laser. Can we transfer what the laser sees into a further range analysis of road? Can we find more of the same? So here's laser driving through a mountain pass, and this is a very, very primitive algorithm finding a trapezoid ahead of the vehicle that is flat, that is wide. So you can see the trapezoid. It's not found all the time, but sometimes. Here we go. And from an image perspective, the way the trapezoid looks like is this thing over here. Okay, the trapezoid is a saw. Okay, you can now train a mixture of Gaussian model to pick up the colors and textures of this blue area over here, and then analyze the image for further occurrence of the same texture. Okay, so everything that's similar to, in a Gaussian sense, within 3 standard deviation of the Gaussian mixture, gets then labeled in red. Okay, and then here's the same from transitioning. So we have our trapezoid coming up at the bottom, and right now, where is it? It's supposed to come up. Yeah, there we go. And it's trained on the part over here. And you see the grass is different color. So the grass initially is not recognized, but as you're on the grass and your laser says, okay, the grass is fine to drive, your learning models change as to what road is. And all of a sudden detect a different color. This is taken from the National Qualification Event, where we frequently cross from paved road to grass back to paved road. And it's really well suited to illustrate this. Here another instance, we're on paved road, doesn't find, as you go into the grass, the laser says it's fine to drive. The only thing that's really happening here is that this region we can find with the laser, so we learn nothing about it, but this is too far for the laser, out of reach, so we can actually now analyze stuff further out and project it further out. Tunnel is interesting, looks very different. It looks clean, not like a drivable surface, but as we get into the tunnel, all of a sudden the tunnel lights up like a Christmas tree, including the side walls, which is a bit of a concern, but they're very dark. And now the outside doesn't work anymore, but as we adapt to the outside, you see the red stuff over here. Now the interesting thing is this is not drivable, non-drivable. It's drivable versus unknown. So some of the stuff that's marked as green could well be drivable. So it can be used for directing the car, but it can be used for slowing down the car. So if in your straight path there is an obstacle, you rather, or some unknown area, say, you rather drive slow enough so that you don't hit this thing. Okay, so here's an unknown area. There's an unknown area. You see the traffic cones really popping up nicely. There's a car over here which pops up nicely. So if this is in your path, then you know that a high-speed laser wouldn't catch it, so you just rather slow down to make the vehicle slower. Yes, yes. And in fact, you can build a car that even humans will hit. Right? In the middle of the night, a car without lights, you'll hit. Clearly, if there's no feature for this car, then you would see it. This is what's called rectification in computer vision. Nothing else but taking this little triangle here that pops up occasionally. This is a very early version. It wasn't very reliable. But you can see the road being detected way beyond this guy over here. And popping into a map. This is each ring is 10 meters, so this is about as far as the laser reach. You can see the dark red stuff is laser. And that's kind of the road extrapolation using vision. And it goes up all the way sometimes to 80 meters or so. So you can sometimes verify drivable surface up to 80 meters. Came in handy when we passed Carnegie Mellon. This is one of my favorite videos. This is slightly out of sync, I apologize for this, but on the left side you see mile 101 in the race, and slightly sped up here on the left side, I think. Back there's an abandoned vehicle called Highlander, which Carnegie Mellon put in the race. It's paused because we're now in the process of passing it. We've kind of been about to pass it many times, and now Darpa gave us the right to pass it, so we paused it. It pops up as an unknown area. That's how a robot looks out of a robot's eyes view. You can see it nicely detected, this thing. And this comes a little bit later, I believe, but here it is. Okay, you can see in the rectified image, there's a fairly solid obstacle. Since this is in the path, the car would slow down. It wasn't a slow speed zone anyhow, so it didn't have to slow down, but it makes for a nice illustration. You can see how this thing is really there, and how the car drives around it. Okay, so that's that. You can do all kinds of measurements, don't read these numbers. One of the things I did is we had multiple vision groups, and they're all competing, and they all want the software in there. One was discriminative, one was generative, and discriminative means you have two classes, good, bad, training, make a distinguishing module, and generative means you have one class, good to drive, and you learn a Gaussian, and everything that looks dissimilar than the good to drive area is labeled non-drivable. And then we set up a competition where we said, okay, we're going to really measure performance. I've become a really big fan of measuring things and really writing it down, like what range, what is your false positive, false negative rate. In the end, the discriminative worked better, but when it failed more catastrophically. It failed usually when you're on a big open flat desert lake where there's no negative examples of negative terrain, and then it becomes very brittle. So we used the generative version, but anyhow, so you can do a lot of side science along the way. Control, last topic, very short. The things you have to do is now steer left and right, or go faster and slower. And I have one more interesting story to tell in the control area that we learned along the way. Steering itself is relatively straightforward. The way a roboticist does it, he rolls out trajectories that a vehicle can physically attain. This is a full dynamic simulation of the vehicle. Given that you want to apply sideward acceleration to the vehicle by steering. Okay? There's limits as to how much acceleration you're allowed to apply, otherwise the vehicle starts fishtailing. You roll these possible paths out, and once you've found a path you like maybe the center one over here, you use a PID controller to follow it, which is superior to reinforcement learning style policies for many reasons. So this is what's happening here, is rolling out these paths and it's building one of those as it drives. You can see the red paths are the ones that are not so good because they run into stuff, green paths are good paths, and as long as the center path is green, it just goes straight, which is very nice and very convenient. Not much to tell other than this took a lot of work to get this all right, but it's essentially a one-dimensional search of whether you want to turn left, right, or go straight. It's a very fast thing. More interesting is velocity control. Slide I made in the office this morning, Michael. Velocity control turns out to be really important going the right speed. There's things you have to obey. For example, Darpa gives you speed limits, goes into the velocity controller. There's also physical limitation. You don't want to go into a curve too fast. You can compute how much sideward acceleration you're willing to tolerate in a curve. But then there's this kind of gut intuition, how do people actually drive? People don't drive full throttle all the time, specifically in the desert. Or if you do, you won't get very far, at least in these desert kind of roads. So we put in a couple of rules pertaining to terrain features, and the most important one were actually the unevenness of the terrain. The desert is full of ruts. If you hit a rut at high speed, it will destroy your car. So the goal was to make the vehicle go slower in areas that are very rutty, so that it would adapt its speed automatically. Happened to be really important. If you develop a car and you sit inside and it goes at constant speeds over ruts, you freak out because you think you're dying. The thing I'm going to talk about is just as one thing of how to use vertical acceleration, how much the vehicle goes up and down, as a way to control speed. Okay? Vertical acceleration is easily measured. We have a sensor called the initial measurement unit, so we can measure it. We can drive the car, but we have to put into a controller. Oh, okay, 4 more minutes. The idea was to use machine learning again and have a rational human driver, Sebastian, drive through the desert, which I did here, and you can see my speed profile as I drove, and find a rule that basically emulates my driving. To find this rule on data, a little tricky step which has to do with the fact I acquire the data at a certain speed, but as I explore different driving rules, the vehicle has to emulate different speeds to understand what the consequences are of driving faster and slower. We found out in the lab that driving over obstacles, the amount of shock you receive, vertical dimension, is linear in your driving speed. So if you don't drive at all, you get essentially gravity pointing down, which is right over here. This is a factor of 10 in the scale of this scale. And as you drive faster and faster over the same obstacle, you end up with a linear relationship. It allows you to take a single drive over terrain and simulate other velocities. So you can try all kinds of velocity controllers offline and pick the one that you like best. The one that you like best had two components to it. Every time you went over something, it would slow down very rapidly. Okay, it's almost the right thing. Sebastian slows down before the ruts, and this thing slows down after the ruts, but still a good rule. And to make sure that if there's multiple ruts, sometimes they come in families, you wouldn't immediately accelerate again. You would very slowly recover to the old speed. Okay, so it's like a forgetful memory. Like you run into something, you slam the brakes, and then you're shocked. Okay, and you're going to be slow for a while. It's like when you get drunk, you don't drink the next night, right? And then you kind of forget, and you go faster. Now we did this, and it did a fantastic job matching my driving, except that my team is of the opinion my driving is not as good as it actually is. So they freaked out having a car drive like me by itself. So we ended up twisting the parameters down a little bit in the end for our final system. Interesting remark, Carnegie Mellon spent a lot of time analyzing data. They had a vehicle going through the same area for thousands of miles before the race, acquiring data. They had a huge data center with about 25 people inside, air-conditioned at the race. So the 2 hours before the race, they could mark every rut using their pre-recorded data. And they slowed down the vehicle manually. And they found it was absolutely essential. They spent enormous amounts of money doing this. We only had this simple rule. And we won in the end. So I can't say this what we did is better, but certainly we didn't have to have this huge data. But this is a video on the web where he explains in length all the steps involved in pre-scanning this terrain. And I sped it up a little bit to make it faster. My last technical slide, testing. One of these, every one of these events, of course, require error-free software. So we spent more time than my wife and I are willing to admit in the desert. It's actually really interesting because we were always in the car. We had an emergency stop button. The car would sometimes drive 100 miles without us doing anything. And at that point, you start reading email, you're chatting. People say, "Look at the road." "Oh, sorry, I forgot." You start trusting the machine. And to me, it's been an eye-opener when I say the future of driving is autonomous, and people will accept it. After a couple of hours of being driven around, it's actually amazingly convenient. And you ask yourself, why on earth did I ever drive these machines myself? It's really interesting to sit in the car and getting this trust. Of course, it wasn't perfect. We put performance measures in. These are measures you find in no paper on driving because people never measure this kind of stuff. But, at the end of the day, we had to get a bug-free system. We had to drive 150 miles error-free. This is our statistics that kind of certifies this to us. We could do it. I don't want to finish without saying doing all this was not without scary moments. If you're in the car and you're wearing helmets, but you're going through cliffy areas, there's moments where you think, maybe it was not such a good idea to do this. So here's my scary moments. There's 10 of those that I want to just briefly report before I close. Number one is actually, I taught a class at Stanford called CS294, and 20 students built the first version of the system. And it was scary because we went into the hardest part of last year's Grand Challenge terrain and drove further than anybody else had driven before, although at slower speeds. And here as part of this, a person is trying to hold his hand as steady as he possibly can, given the accelerations in the vehicle, and look at the steering wheel and the terrain behind. And there were some very serious cliffs. So there was a different form of grading homework assignment, where I, the grader, actually sits in the car, and if I don't survive, there's no grade. But I can tell you it was scary. You might not feel it as scary, I was inside it. This is July in the desert, another scary moment. You'd think it would not rain in July, but rain in the Mojave Desert is very binary. It comes delivered as a big bath with like a couple of inches of rain on one day, and then it doesn't rain for the next 4 months. So this is the old course underwater. And the scary thing is the car has its wipers go on automatically, so you sit inside, but they're not sufficient to basically get all the water off. So the only way, the car is driving itself right now, the only way we could actually see if the car is something useful is look at the computer screen and see if these obstacles pop up, and we see the bushes on the side. And Mike would say, yeah, it's fine, it's seeing the bushes, and so keep driving. You sit there for extended periods of time seeing nothing. The video is not doing a good job. It was actually worse, the car. Okay, so Sometimes cars drive better than people. We got stuck the same day, had to dig it out. Okay. This is most of our crashes. We had two major crashes happened with television or journalists in close proximity. This is a television team actually taping one of our crashes. Here we go. And we fell down in a ditch. It was this mapping bug that I reported earlier that we then fixed. Okay. Very embarrassing. Scary moment number 4. Scary for me more than it'll be for you. It's data from our race itself. When I went through the data afterwards, I was really surprised to see that the course that Darpa had given us was significantly off the road. I mean, we expected this is a 20 centimeter accuracy GPS, so they should be perfectly aligned with the map. But what you see is the course that Darpa gives us doesn't align with the map at all at places, and we have to really drive at the very corner of the legal course as happening over here. That to me suggests that any vehicle just following GPS wire points would have zero chance to survive this. Now, one of the scary things to me was dynamic obstacles. In fact, the way we interpret data, every time you see something in the sensor data, you think it's an obstacle, right? So a butterfly flying by is an obstacle, a tumbleweed is an obstacle. I remember we drove in the old course and a farmer had just put a new crop on the farm, a seed, I guess, and the birds all came to eat it, and they're still on the road, right? And you come up with a big car, and they all fly up, and they become a big wall of obstacles. Car goes crazy, it slows down, birds sit down 10 meters away from the car, accelerates again, same procedure. It's really frightening. In the race, actually, the chase team reported to us an incident whereby a bird flew by. And you can see it over here. There was. And here's the car swerving as a result out of nothing. I can tell you, I know exactly every butterfly in the Sonoran Desert at this point. And we swerve for every butterfly. We weren't the only one with scary moments. This is a video from Blue Team in Berkeley, one of the training videos. You can see the guy doing nothing as the vehicle descends into a lake. Okay, kind of a sad moment. Rescue your robot. A little bit later, this is the way you clean a robot after. So Berkeley had another set of interesting maneuvers. This is one that it did posted just before that. You can get it on their website. It's their famous flip at 36 miles per hour. And they actually taped it. It's amazing. So you can see it in slow speed. It's quite amazing what you can do with a motorcycle if you don't get your controls right. Later they actually used reinforcement learning for this, and it worked much, much better. But this was one of the earlier attempts to control a motorcycle. I have to admit, I admire these guys for what they did. I'm going to be in record of saying this because it's incredibly hard to control a motorcycle under conditions like these. The flip is actually not a Berkeley maneuver, it's more a Carnegie Mellon maneuver. They, a week before the race, flipped their leading vehicle, and this might actually well be the reason why they didn't win, because they had an engine problem in the final race that we benefited from. They did this maneuver invented last year, 2 weeks before last year's race. They flipped their car then, and also got into a big scramble. Again, a control error. What surprises me is this is completely flat terrain. There's absolutely no way something else could trip the vehicle. So they must have had a severe control error last year doing that. Scary moment number 9 from the race itself, from the qualification event. Some of the vehicles were not as good as others. This is Team Jefferson. And the builder told us that when it crashed, it was 60 miles per hour fast. It's very hard to see, but you'll see it. You'll see it twice. There it goes. Okay? And look at the guy on the right side running away. We had to get an ambulance in, and he had a couple of wounds. This is the car itself. It was kind of totaled. And the people who spent more than a year of their life building it, somewhat desperate. But this was an accident without these concrete barriers could have been fatal. And as a result, Darpa removed almost all the viewing platforms in the race itself for journalists because they didn't want to kill journalists along the way. Scary moment number 10 is this one. This is our friends from Caltech. They did this very conveniently exactly where the journalists were located, so they could take fantastic pictures. Here's the video of that. And you can see Caltech doing some heavy concrete barrier action. Persistent, yeah, until Darpa stopped them, which was thanks to the journalists. What's next? I actually honestly, I asked this question before, and you can tell me your opinion. I honestly believe that we have cars to drive themselves will be of benefit to all of us. They make our act of commuting more productive, and they eventually make us safer. So what we're doing is we're building a system now that hopefully 2 years from now can go from San Francisco to Los Angeles in real traffic. So if you're in the area and you see a Passat coming by, driving slumbered erratically because there's a butterfly, then it's us, okay? So don't bring butterflies to the area. Luckily, there's not that many butterflies. But I mean, I made all the points. I think I wasn't a car enthusiast before this, but now that I see what we can do with robotics technology in this sector, I think we should all start thinking about, this is big. This is more than a robot that brings you a cup of coffee, or other ideas I've seen in AI labs, like bringing you a fax to your office. This has more impact. It makes elderly people maybe driving that otherwise can't drive anymore. And the moment people give up driving in a high age, they lose their social relationship, they become dependent, and they decay very, very fast. You can show that the moment they give up driving, they basically will be dead a year or 2 years later because of this. That might enable people to do things they can't do right now. A lot of great visions. So we are now determined to take the success we had and put it on the road, deal with other traffic, understand it, and push in this direction. With this, I'd like to close and ask for questions.
I've got like a whole set of questions, and I think everyone else does too.
Take one.
You also have access to them later this afternoon in the other group.
Oh, okay. I'll ask later then.
Okay, that'd be great.
Ask your first question.
Okay, so you were talking about the tilting problem with getting these things. Now, part of that's because you have a set of 5 lasers all set to different heights, and they're all doing this time integration, trying to figure out what the height is. Did you think about putting like some kind of gimbal scanner to go over check those previous?
Oh, this is great. It turns out that every time I give this talk, this is the question number 1 I get. And we discussed it. It turns out the problem of estimating your exact angle is not resolved by gimbal. Okay, you still have to estimate your exact angle. If you make an error in that estimation, you still run the same problem. What you do solve is to get a more stable input. Now it turns out gimbals are relatively complex mechanical devices, and to build them well takes a lot of expertise. So we didn't feel comfortable building a gimbal on the offshoot it might actually break during the race. As did, by the way, Carnegie Mellon's gimbal broke during the race, which was a big problem for them. So our idea was, rather than putting complex mechanics in there, put smart software in there. And as you could see, we compensated the problem in software just fine. The reason why we used 5 lasers, you can think of this as a very cheap primitive gimbal, which is no matter which way the vehicle is oriented, no matter which way the course goes, we always have a laser at hand that gives us the data. And that's a choice. I mean, you can debate it. I know Dickmans, the guy in Germany who was the prophet in all of this, really was upset that we didn't have a gimbal and said you can't win the race without a gimbal. And I said we can win the race without a gimbal. I sent him an email afterwards saying we did win the race without a gimbal. I'm sure if you had infinite resources and a top-notch gimbal system, I would have used it. And it wasn't necessary.
Even though Dickmans has done a lot of, tunnel driving, but in roads were well paved.
Right.
What's your challenge? I mean, say you want to drive from San Francisco to...
So again,
basically, I haven't seen him doing with a lot of traffic.
yeah, so there's a person in Germany, Ernst Dickmann, who did fantastic work in the mid-80s, mid-90s on highway driving, and he drove a couple of 100 kilometers vision-based only in German traffic, which is even harder. I don't think the problem is solved. I don't think we have reliable systems. Most of the people that do this report something like, 98.5% of the way the system was autonomous, and 1.5 I had to actually assist the system. But if you look in detail, what this entails is, phone call. Just stop myself here, ignore. What this entails is that every half a mile, every mile, you have to correct your steering a little bit. And that doesn't mean the person can fall asleep. I think methodologically, I want to move away from pure vision-based and reactive to much more database-driven, GPS-driven, and so on. I want to really get a system that reliably drives 100% autonomously. Yes?
So what could you do without GPS?
Nothing. It was all GPS-based. I mean, there's places where you have no GPS, like drive through a tunnel, and you drift slowly away, so we can control for this using a vehicle model. But in this specific race, GPS played a very primary role in all of this. For example, you could not find your own road. Without GPS, you would not have a GPS corridor to follow, so you had to find your own road. I I'm not making any claims that we could do that. Yes, very good.
Do you have any thoughts about how you're going to be able to beat rain and snow and fog?
Rain is not as much of a problem as we thought it was, given the right sensing. And we are now thinking about moving the sensors inside the driver's compartment so we can use the regular wipers to help us with things like rain. Snow and fog, you know, at some point when your sensors can't sense things anymore, like lots of leaves and so on, you run into difficulties. You know, I'm a little bit troubled by this question in the following sense. I'm sure you could have walked up to the Wright brothers and say, you know, you guys can't fly across the Atlantic. And they would have said, you know, honestly, we don't know how to fly across the Atlantic. To some extent, this is just a small step along the way of building autonomous cars. So this is something we have to explore further in the future.
I'm not criticizing them.
I know.
If anybody would have an idea, it would be you.
Good, thank you. But, so, it turns out the sensors are amazingly survivable even under things like fog. So we did fog tests. We had, not fog, we did dust tests. So we had 2 cars in a row. The one would stir up dust like crazy, brake all the time. The second one would follow. And the second following car had no difficulty seeing 20, 30 meters out. Snow, I've never tested because I live in California. I guess you have snow here. It'll probably require a number of different sensing modalities and very smart software to accommodate this, which we haven't touched at all. You only have sunshine in California.
Captain, just asking this maybe last question. So after Stanley won, so the drive to Disneyland?
Yeah, I mean, what happened to the car?
Yeah.
Or, so Stanley has become a major marketing thing for Volkswagen. In fact, they estimate multi-million dollar, multi-tens of millions of dollars of revenue because of this. In fact, if you opened the USA Today about a week ago, there was a one-page ad this big on like page 12 in the first part saying like Herbie meets Stanley, and it was congratulating Stanford and so on. It's kind of clear that neither Stanley 1 nor Stanley 2, we have 2 cars, will ever drive them. They go from show to show. Thursday I'm going to meet people from the Smithsonian Museum. They have expressed strong interest. They might take it temporarily or permanently. I mean, it's hard to say. Some people say, you know, we made history. Feels good, you know. The Wright brothers were very often mentioned in the same article where they talked about us. But maybe we didn't have similar challenges in the last couple of years, and people like to hype things. Maybe it's an unimportant event, and we find out that driving on the road is so much harder, and it's just deceptive to think of this as an achievement. We don't know, but the interest right now is huge. I mean, both cars are continuously on shows. One is in Germany. They get flown across the Atlantic regularly, and so on. It is sad because I lost my lab instrumentation. It should come in second. Anyhow, thanks everybody.